everyone, and thank you for attending today's webinar, Programmable Infrastructure in Edge Computing, Unleashing Scalable Innovation, sponsored by Lanner, Fortinet, Noviflow, and Barefoot. Before we begin, I want to cover a few housekeeping items. On the right-hand side of your screen is the Q&A. If you have any questions during the webcast, you can type your question into the Q&A box and submit your question to our speakers. All questions will be saved, so if we don't get to answer you, we may follow up via email. At the bottom of your audience console are multiple application widgets you can use. If you have any technical difficulties, please click on the yellow Help widget. Here you can find answers to common questions. A copy of today's slide deck is available for download in the green resource list widget. Towards the end of today's presentation, we'll ask for your feedback. A survey will pop open on your screen and will only take 1 minute to complete. Your feedback is extremely helpful. An on-demand version of the webcast will be available about 1 day after the event and can be accessed using the same audience link that was sent to you earlier today. I would now like to turn the event over to Heavy Reading Principal Analyst, Cloud Infrastructure and Edge Computing, Jennifer Clark. Jennifer?
Thank you very much, Beth, and welcome everyone to today's webinar, Programmable Infrastructure and Edge Computing, Unleashing Scalable Innovation. As Beth mentioned, my name is Jennifer Clark, Principal Analyst at Heavy Reading. I'll be your moderator for today's webinar. My son won't be up for a couple of hours. I've kicked the cat out of the office, so fingers crossed I'm good to go, as is our distinguished panel of speakers. So let me start by introducing today's speakers. In addition to myself, we have Prem Jonalagada, Senior Director of Product Management and Marketing at Barefoot Networks, which, as you know, is an Intel company. Sven Freudenfeld, Chief Technology Officer in Telecom Applications Business Unit for Lanner Electronics. Jesper Eriksson, VP of Product Management at Noviflow. And Nicholas Tomas, Standards, Mano, and VNF Strategist at Fortinet. We have a very busy agenda, so let's get right to it. I'm going to be starting with a few of the insights from Omdia to set the stage. I'll be turning it over to Prem, who will be talking to us about the programmable network fabric. He will then hand it over to Sven, who's going to be talking to us about converged MEC Smart Edge platform. Then Jesper, who will be talking about network operating system O&M and MEC platform software. And finally, Nicholas, who will be speaking to the issues of virtualized scalable security software. We'll then provide a summary and open it up for Q&A. I will be doing my best to keep our speakers on schedule, but we have a wealth of great information to cover, so let's get started. I wanted to set the stage of the environment that we're talking about as we enter this era of mobile edge computing. First, what's changing? It's tough to put your finger on the number of data centers, but we understand as we move into 5G and as we move into an environment that's characterized by IoT, by very high-speed broadband, by low latency applications, that we are increasing the number of data centers. If we just use as a measure the number of 5G data centers, we can look at today's environment, which has over 6.5 million physical base stations, and that doesn't include multi-sectored antennas, which could increase that number by a factor of 6. And as we move into 5G, we have a conservative estimate that we will be increasing that number of physical base stations by at least an order of magnitude. And at each of those base stations, we're going to be having both compute and storage capability to handle some of the video applications that are going down to mobile devices and a wide variety of IoT applications as well. If we look at the percent of workloads that are in the cloud, we are seeing, as we move to HR, support, sales, all of these very large enterprise workloads that have been traditionally in centralized data centers, all of these are moving into the cloud. If we look at the data from one of Heavy Reading's global enterprise surveys of over 1,000 enterprises, they are expecting 22% of their workloads they saw in the cloud in 2019, but half of all these workloads will be in the cloud in 2024. If we then look at the number of connected devices and just look at the number of IoT connections, when we examined the IoT connections of our top 10 communication service providers, they saw over 400 million connections in the first half of 2017, over 1.2 billion in the first half of 2019. And if you look at the share of machine-to-machine connections, it will grow to over half of all connections within 4 years. And that amounts to about 15 billion machine-to-machine connections by 2023. Then if you look at low latency connectivity that is supporting a wide variety of delay-sensitive applications, both on an industrial side, on gaming, for gaming applications, and a wide variety of M2M type of applications, including a lot of the ones that we're seeing in our automobiles. They're going to be relying on the low latency application, the low latency connectivity that comes with 5G and with advanced broadband communications on the order of 1 to 10 milliseconds. Now, if this is what is changing in the overall applications and demand side of the picture, what are we dealing with on the network side? We're dealing with a network that is, in fact, fairly flexible, but nevertheless is still very hub and spoke topology oriented. We're dealing with OSS, BSS systems that are extremely full-featured, very functional, but nevertheless tough to change and and not that flexible right now. We're dealing with a lot of hands-on network management that cannot possibly scale to meet the number of devices, the number of data centers that we're talking about on the left side of the screen. And we're dealing with enterprise security that's grown up in an environment of known threats, or at least known attack vectors, not in this zero trust environment demanded by today's borderless enterprise network. So without the type of telemetry and predictive maintenance, what we're seeing on the right side of the screen is not going to support what we're seeing occurring on the left side of the screen. So with that, let me turn it over to Prem, who will talk to us about the programmable infrastructure.
All right. Thank you so much. Hi, everyone. This is Prem Janwagada. I'm a Senior Director of Product Management and Marketing at the Barefoot Division at Intel. And today I'm going to talk to you about one of the key components in the Lanner platform, HTCA 6600. I'm really excited to be here and be talking about this because over a year ago, when Sven came to us and presented the idea of building this platform and using our Tofino switch silicon as the fabric, as the switch fabric, we were seriously quite excited about it. And it's really good to see this platform coming to the market. As Jennifer was saying, you know, the requirements for the mobile edge computing are quite different and varying, and they're going to affect all kinds of different use cases. So you really need a programmable switching fabric in this platform to be able to adapt and change to the varying needs and deliver new services at the speed of software. So let's take a quick step back and look at this general industry trend that has been taking over different verticals of the technology industry. I mean, if you look at the computing or graphics or signal processing or more recently machine learning, there's this trend where there's the domain-specific high-performance target processor and a high-level domain-specific programming language. These two are brought together with a world-class compiler, and together they give the control into the user's hands. Application developers can develop applications that they need to, and infrastructure builders can deploy applications on these target processors as they see fit. So you can see that this paradigm of domain-specific architectures brings a lot of benefits, and that's why they become predominant. Now, until we came on the scene, if you look at the networking industry, especially the high-performance side where there's multi-terabit of switching, it's been predominantly held hostage by fixed function ASICs, which gave the high performance, but it was very hard to change their behavior. I mean, you cannot change their behavior. You have to wait for the next generation silicon to come around to take advantage of any new features. So what we have done as Barefoot Networks startup started this really important trend in the networking industry, where we brought the networking industry to this domain-specific architecture paradigm. So a couple of things that needed to happen. One is, yes, you need to have a high-performance target processor or an ASIC. So that's our Tofino switching silicon line. And then, more importantly, you need to have a high-level programming language, and that is P4, which is an open programming language. And we built a world-class compiler to bring these two together. Now, the builders of network infrastructure, can reap the benefits of this domain-specific architecture by taking advantage of Tofino and by writing code in P4. So the two key components. The first one is P4. So P4 is an open programming language that is, brought together by a community, a strong community. There's over 3,500 and more developers trained on P4. There's 5 active working groups discussing various issues and various features of the language, application development, language evolution, education, so on and so forth. And there's over 100 member organizations that are working together to make this programming language a success. So we've seen quite a bit of uptake and adoption for this language across the board, cloud and communication service providers, OEMs, ODMs, open source networking projects. So it's really exciting to see the adoption that P4 is getting, not only in the switching space, but across the board, even in network interface cards, soft switches, and so on and so forth. So strong and growing ecosystem for the open P4 programming language. Now let's take a quick look at the products that we have built at Barefoot. So Tofino and Tofino 2 are the switching silicon. We also have a network performance monitoring analytics software. The product of interest for today is our Tofino switching silicon, which is fully P4 programmable and can go up to 6.4 terabits per second. So what are some of the benefits of these P4 programmable switching ASICs? First and foremost, when a fixed function silicon is built, it's usually built to address multiple different use cases. So there's a lot of hardwired code in this silicon, which is not used by everyone because it's a union of all the features. With a programmable switch, you can actually strip out complexity and make it simple and just implement the features that you need. One of the key features that our silicon is providing is this real-time data plane telemetry, which gives full visibility into your network with a feature called in-band network telemetry that we worked with the P4 community to develop. Now, another artifact of simplicity is more scale. So when you're implementing only simple, only the features you need, you can derive more scale for the features that you've implemented. Because it's programmable, you can actually adapt and innovate at speed of software. So any feature you need can be developed in P4 and be deployed at the speed of software. And again, as requirements change and new protocols come into picture, you can actually implement those and deliver them. So your platform becomes future-proof. So one of the big advantages of the programmability is the ability to connect various, target processors, whether it's CPUs, FPGAs, GPUs, AI accelerators, it doesn't matter. Any of those can be connected because they're a fully programmable nature of the P4-programmable ASICs. And we are seeing adoption across access, edge, core, data center, and cloud. So let's look at the use cases for some of the P4 programmable switching. So yes, definitely we can do the standard switching and routing, but we can do it much better. So the platform takes advantage of the enhanced switching and routing features. On top of that, you get the real-time telemetry, which is very critical for delivering, services with high levels of uptime. And then beyond that, there's a lot of emerging applications that are being looked at and brought to market. Things like layer 4 load balancing, security, DDoS detection, 5G gateway, and tunneling, various types of tunneling, and so on and so forth. So it's really a fully programmable fabric that connects your compute nodes and allows you to scale and adapt as the requirements of the networks change, thereby unleashing scalable innovation and edge computing. So to talk more about, I think, the platform and more details, I'll hand it over to Sven.
Thank you, Prem, and welcome everyone to join the webinar. What we are looking at is the network infrastructure and the directions where the concept of disaggregating the network is taking place. So I want to cover a couple of options on how to make this technology integrated to work, and as well, some of the use cases, how the scalability aspect and the dynamics of using P4 programming as well programmable pipelines, an important feature for some of the use cases for multi-access edge computing. As we see the trend in the market, there is a conversion between fixed networks and mobile networks. And fundamentally, it's really combining not only all the compute aspects for the network, but more importantly, the networking aspect in the network. So combining both network capabilities, scalability, to be able to deploy VNFs very dynamically, as well be able to scale to run multiple functions in ideally in a single platform. Typically, with deployment, what we see today is each function has a dedicated platform, a dedicated hardware, with the network function as well the switching fabric built into it. And it's not very efficient moving towards the trend of consolidating network functions, but also by looking at supporting multiple functions on a single network element. If we would focus and move forward with proprietary conceptual architecture, it will be very costly, and at one point will not be longer sustainable in order to scale the network, especially on the edge. So what we're looking at is, in more details, is really at the network functions for the edge compute sites, meaning that how we can deploy, multiple network functions like virtual firewall, virtual BNG, virtual PE, and other network functions on sort of a agnostic programmable white box approach including computing, networking, aggregation, and storage. So when we look at the overall network topology at the edge, the most dynamic workloads are typically at the local aggregation site. That means that we have to the left on the access side, there are different type of devices, many different type of devices. It might be an SD-WAN device, it might be a universal CPE device, it may be a baseband processing unit for Xeon applications, or it may be also IoT traffic. So the lower end networking paths coming from the access side can be very dynamic and very different with different policies and different network requirements. At the aggregation side, the main requirements are number one, being able to create networking paths which are more dynamic than at the core or at the metro network, as well be able to scale at the aggregation side. So we need to be able to spin up virtual instances to deploy multiple VNFs, and depending on the network load, we need to be able to scale that rather than passing traffic to the metro network or to the core network. Given the fact that the workload is most dynamic at the local or at the aggregation layer, that means we need to have a infrastructure for the switch fabrics, which can be changed dynamically. As well, can be separated in multiple segments in order to deploy potentially 5G network flows within the network. And giving the technology, what Prem mentioned earlier, gives us many different tools to be more efficient at the edge. So the Barefoot Tofino, the combination of the Intel Barefoot Tofino and the Intel Xeon, next generation Intel Xeon compute nodes, gives the framework to provide programmability at the edge. That's where, as I said, that's where the most dynamic workload is. We need to be able to repurpose the same infrastructure for different workloads, but also to introduce better visibility. You need to be able to be more efficient by dynamically rerouting traffic within the network before it hits the metro or the core. Because if you wait until the packets are heading towards the core network, it's too late to make the right decisions for the network flow. So the inbound network telemetry is a very important aspect for edge computing, multi-access edge computing, and as well the scalability aspects on that. So most of the initiatives we see today lagging on the actual aspect on the networking aspect. So that's why we built a solution, a framework which provides programmability, visibility, as well scalability for compute resources. Looking at some of the use cases, we see multiple applications coexisting on the same physical hardware. Edge compute size is typically limited on space, power, and cooling. So we combine everything into a single platform, and we are able to scale. So we can spin up new instances using an SCM framework, and we can deploy either a virtual firewall, virtual BNG, virtual DDoS applications, and many others very dynamically and quick. What it does is eliminating the overhead cost for operations, meaning all the truckload to traditionally send people on site, doing installations at the telco closet at multi-dwelling units, for example. This is an example for multi-dwelling units use cases. And it's dynamic and it can be done very quickly in a short period of time. So it saves a lot of operation costs, but also is more efficient in repurposing and changing the workload and the virtual network functions dynamically. without the need for shipping additional hardware platforms and elements. So if you look at the overall architecture, we have a quick overview on this. It's a platform which is consolidating computing, networking, storage, aggregation, fully managed remotely. And we can scale up computing and networking, a very important aspect on this in this seminar. But there's, there are a couple of elements in order to make it really a true software-defined infrastructure. The first one is the Barefoot Tofino, which is based on Intel Barefoot. So it allows us to really bring the openness towards the edge compute platform, rather than being hostile, as Prem was saying earlier, into a specific silicon. We provide the flexibility and the scalability. And also we have the capabilities to add functions for use cases for, let's say, CRAN applications where timing and IEEE 1588 is an important aspect onto it. And in order to leverage all the underlying hardware elements and resources, we of course need to have a partner or a team on putting it all together on the software side to be more efficient. So I'm handing that over now to Jesper.
Oh, thank you very much, Sven, and good morning, everyone. This is Jesper Eriksson, VP of Product Management at Noviflow. So Noviflow is porting two of its existing software products to the Lanner HTCA platform. The Noviflow NOS, running on the Switchblades, and the CyberMapper application running on two of the compute blades. Noviflow has also developed a new software product specifically for the HTCA platform. It's called Visual Analytics and resides on the compute blades as well as on the mass storage. A few words about Noviflow. It's a mature SDN switching NOS that's been in commercial operation with carriers since 2014. It has a full range of modern O&M interfaces such as GNMI, GNOI. It supports P4 runtime and OpenFlow northbound interfaces. And this allows you to configure and dynamically update the packet processing in the switchblades. And essentially, it allows an application programmer to define a unique match action pipeline to match the requirements of his or her application. Next is CyberMapper. CyberMapper is an application built on top of Noviflow. It's in commercial operation with multiple carriers around the world. On a high level, CyberMapper provides the following services: threat intelligence, gateway services, traffic steering, packet brokering and filtering, sticky and stateless load balancing, SRv6 routing, and service chaining through SRv6. And then finally, Visual Analytics. This is a new standalone application from Noviflow, first released on the Lanner HTCA platform. It provides an end-to-end view of the HTCA platform for hardware and software alarming and troubleshooting. It simplifies the O&M, and with potentially thousands of these MEC platforms deployed in the network, you want to find ways to minimize your truck roll, and that's one of the intended purposes of Visual Analytics. And also, if you have to go to a site, it would be very good if you could do preventive maintenance when you're there. So I will now talk in more detail about CyberMapper and the Visual Analytics applications. CyberMapper, as I said, is built on top of Noviflow and provides a number of services that operators need in their network. The Threat Intelligence Gateway service is a way for operators to block certain traffic to get onto their networks. CyberMapper will execute any blacklist directly in the Tofino silicon and do so much more efficiently than on, say, an x86. An example of a blacklist is the blacklist published by the Internet Watch Foundation. The packet broker services include things like filtering, mirroring, and port pairing. And the load balancing services are built on top of a sticky and stateless load balancer implemented directly on the Tofino silicon. It supports proportional load balancing and the ability to dynamically grow and shrink the pool of load balanced devices. For the Lanner HTCA platform, the load balancer leverages the two NICs on each compute blade and uses SRIOV for maximum throughput performance. The networking services include traffic steering and aggregation for scaling, say, CGNAT and other services, in-band network telemetry for VNF performance monitoring, and then SRv6 routing that allows the VNF resources inside the platform to be globally addressable in the network. The visual analytics provides an end-to-end view of the hardware and software status of the platform. This simplifies the operation and maintenance of the HTCA platform and saves money. For example, a single truck roll may cost in excess of $1,000 per instance, and this tool allows you to minimize that and avoid unnecessary truck rolls. And it also allows you to do preventive maintenance to be scheduled to replace failing parts such as fans and power supplies. So how this works is that the visual analytics software harvests thousands of data points each minute from the hardware, the compute blade operating systems, and the Noviflow applications. This data is transformed into its canonical form and ingested into a data lake residing on the platform. The data is then organized and visualized for easy troubleshooting, and it allows you to identify key hardware and software events, correlate events, and also drill down into specific events. A little about the high availability functionality. This has been the key principle of the design, and we provide multiple levels of redundancy. The Tofino switch blades are duplicated and operate in active-active mode. So traffic from the outside is load shared across the two switch blades using lag. If one of the switch blades fail, the traffic is redirected to the remaining. The CyberMap application runs on two different compute blades in an active standby mode. And then finally, the virtual security appliances run on the compute blades in an N+1 or N+M mode. So if one of the VNF fails, the traffic is redirected across the remaining VNFs. Now over to some of the use cases for this. And the first one is a scalable security parameter. The HTCA platform may be deployed as a bump in the wire or as a routable member of an SRv6 network. Excuse me. What this means is that the security services are either hardwired into a particular location or globally addressable through the router network. Traffic enters the HTCA platform through the Tofino switch blades and then load balanced across the VNFs. Capacity may be scaled up or down dynamically, and the VNF latency measured through in-band network telemetry. With the compute resources available, we estimate the following Fortinet firewall throughput performance: more than 900 gigabit per second of pure firewall throughput, more than 400 gigabit per second of IPS, and more than 350 gigabit per second of firewall plus IPS. The next MEC use case is edge aggregation. And this use case is architecturally different than the previous use case, because in this case, the traffic enters the HTCA platform through the I/O blades on the front directly into the compute blades for processing. There's no load balancing, and each subscriber is connected to its own dedicated VNF, or in this case, Fortinet FortiGate. Once the VNF has processed the traffic, it is sent to the Tofino switchblade for forwarding further into the network. With the compute resources available, we estimate more than 900 gigabit of throughput and the ability to host over 500 instances of the FortiGate. Then the last use case I'm going to talk about is SRv6 and service chaining. Traditionally, security appliances have been hardwired into specific location in the network and only available for traffic going through that location. And SRv6 opens up a new way of programmatically insert security services in traffic flows that are not tied to a specific location. In this use case, the HTCA platform operates as a security service proxy in a routed SRv6 network. A source router somewhere to the left in the picture will insert a segment routing header with a list of segment IDs. One of these segments represents the security policy that the packet has to go through. The source router then forwards the packet to the next hop. Once the packet has been forwarded to the HTCA platform, it will map the segment ID into a specific chain of security services and then execute them before forwarding the packets to the next hop. So Lanner and Noviflow are working with a major North American carrier and tier 1 router vendor to build this architecture end to end. And I will now hand off to Nicholas Thomas from Fortinet.
Thank you. Next slide. There we go. Thank you for this wonderful introduction on the hardware part. I'm going to show you a little bit more on the application vision of using those platforms. And I started by a couple of use cases. The platform is very, very usable in many cases, adaptable. So we can think of doing many things, but we decided for this webinar to go through a couple of use cases to make things more interesting. But there is much more than we can envision when we start to work on those things. So the first one is really to map on those front panels and having a very strong customization at the edge in a very compact format, linked to every customer's any site, which allows MSSPs, for example, to have a very dedicated customization in that form, meaning that you don't need to deploy the same hardware and the same config, but you can really customize per customer, per use case. You can have an IoT VM or an IoT domain inside for the same customers, etc. And we also see that we can do a lot in what a next-gen firewall and the Fortinet firewalls can do, because many people confuse filtering and firewalls. A well-configured firewall can do antivirus, data leak protections, anti-malware, and phishing, advanced threat protections, etc. So detecting also bad behavior, malware that's not on our signatures, but that is actually detecting live was some of the suspected files going to. So it allows one is to really customize, and that is why you have the traffic coming in, the blades, and then the FortiGate products directly, and allow these separations and strong separation between customers. Another one very interesting for the scalability issues is CGNAT or set gateways, where there is a lot of seasonality, especially the set gateway in Europe, for example, where the Commission changed the rules for billing, and now everyone is using their data on roaming. That means for operators, there is a lot of seasonality with that traffic. And the capability for us to provide solutions with our partners for a scalable solution, and then we use the rest of the platforms for doing other things like virtual reality or any other use case is very, very key. With the different tests we've done together, and the upcoming target is to reach 1 terabyte, which is not something you get from small boxes It's very hard to get a 1 terabyte NIC. And thanks to some of the very advanced features we developed in FortiGate for public cloud and the horizontal scalability, we can reach that with only relying on the P4 and the Noviflow for the load sharing, load balancing, because we can do session sync. And with this combination, we can really reach a very high throughput, which is what most service providers, customers foresee will be needed even at those edge. Some people started to edge and things very small, but we realized that in reality, it's getting in the terabyte per second type of traffic in a very rapid time, and a lot of IP sectors, a lot of security capabilities that requires a lot of resource to at those edge. And here we only focused on pure security services directly. But if you try to secure something else, if you try to secure virtual reality, and we did some of those POCs with AT&T at MEF for protecting that, you really also need to stay in the way and in the path. Otherwise, you will increase the latency when you add the security after the fact, and you lose the benefit of getting in the edge. So it's really critical to be able to adapt and to scale on those platforms in a very, very orchestrated manner. So the result and the expectations, when we tested so far, we reached 200 and more gigs, but we were limited by the lab equipment. We foresee when we will be able to have the support for the 25 gig mix on our side to reach the terabyte target. Then we can. I'm not going to open a debate on what measures for security looks like, because it can be a full webinar just on that subject. But we are pretty confident in that sense. And when you go through inside the box, inside what's going on, of course you have an orchestrator, API driven. Of course, we are all API driven, so it's all API everywhere. And you need an orchestration layers can be adapted to many of our customers' choices of orchestrations and operations to reach that. We had for demos developed some of those ourselves, but in reality needs to integrate with the orchestrator of choices. Again, I choose to use a very dedicated use case that we use to validate the throughputs and the scalability, but we foresee many more use cases, especially when you combine the security and you add the security to your IoT or virtual reality, advanced augmented reality use cases, where you need to be on the same platforms to keep your latency at a correct numbers. And with that, I will hand over back to Sven.
Thanks, Nicholas. Given the fact that we laid out some of the use cases into the scenario for multi-access edge computing, what we see as a deployment model is typically, one scenario is we see happen is at the branch level, at the customer premise equipment, this is mainly moving forwards towards white boxes. And we have seen that picking up very quickly and, really being adopted in the network, where one single appliance is sharing workloads with multiple different VNFs on the customer premise side. The next portion here is the Edge Central Office, and that's really where we combining the networking aspect as well as the computing and aggregation aspect on that, because that's the critical path in order to grow the deployment of customer premise equipment as well baseband units, processing units, and so on for Xeon applications, for example. So the Edge Central Office is becoming a critical element in the network, and therefore the combination of all the different elements and being software defined is a key differentiator here. The traditional data centers are different scale. As I mentioned earlier, most of the time network aspect is fixed at one point and doesn't change as dynamically as at the edge CO, and as well, compute resources are on a different scale than at the Edge Central Office. So we consider this platform really as a mini data center in a box to addressing the edge and the aggregation side for multi-access edge computing. And then if you look at the use cases, typically when deployments takes place, if you have dedicated hardware elements, even though if you use some of the SDN framework, you still have a lot of overhead in terms of cost as well, the operations aspect, because every time you have to do a reconfiguration of a network, you may or may not have to send a track roll to do changes in cabling, and as well to reconfigure some of the platforms in that aspect when proprietary platforms are in the mix of that. So what we really try to address here is that we can reduce the overhead for MEC deployment, multi-access edge deployment, significantly by combining a software-defined networking aspect with compute nodes and providing scalability on the platform compared to the overall deployment with dedicated separate entities in the platform. What that means also is, from a operational aspect, we're saving about 89% of the cost for the overall deployment. Just thinking about deploying all the networking interfaces from a proprietary dedicated switch fabric using all the QSFP, SFPs, and so on. These are very costly. And then secondly, having a technician or a field engineer being on site all the time by changing the dynamics at the multi-access edge compute side, that's very costly. And just the fact that we're combining everything together is also bringing a savings of 75% on space. Very important for some of the deployment with multi-dwelling units or even locations where space is very limited. And also the power consumptions, of course. If we are able to reduce the power significantly by integrating multiple appliances and network functions in a single modular appliance. And never, not to forget about the cabling. Big aspect on that. It reduces, with our solutions, we're reducing the overhead on the operational aspect, reducing the overhead of additional modules into the platform. So we're scaling really everything down to a more usable use case as well, business case for deploying multi-access edge compute platforms to bring scalability and programmability to the edge. And with that, I'm handing it over to Jesper.
Well, thank you, Sven. To summarize today's presentation, we like to highlight the following. So the HTCA platform, as presented today, offers an all-in-one, scalable, zero-touch, and software-defined MEC platform. It leverages Intel Silicon for both compute and networking. The HTCA platform is ready to deploy. And to get there, Noviflow is taking the system integrator responsibility for the entire software stack. And you may use an existing VNF from a list of already integrated and validated partners, or engage with us to let us know what you'd like to see on the HTCA platform. The platform is future-proof. The entire layer 2 to layer 7 is programmable. The switch blades are built on the Intel Barefoot Tofino chip, allowing us to update the packet processing in the silicon as requirements evolve. A good example of this is how Noviflow recently added SRv6 support in CyberMapper. Everything else runs on Intel x86, allowing the functionality to easily evolve as requirements evolve and change. And we estimate the HTCA solution to have an 89% reduction in CapEx compared to using traditional standalone servers, load balancers, and switches at the edge. We also estimate dramatic OpEx reductions from power, space, and O&M. And with that, I'm handing it back to Jennifer.
Thank you very much, Jesper. And we are ready to open up for Q&A. We have received a number, so and we do have a few minutes to take these. So let's start with a question for Sven, which is slide 29 says computing at the edge is low cost. Why would it be lower cost than in the core data center, which has enormous scale efficiency?
So the edge is as I mentioned, the edge is the entry point of the devices connected to either a business or a customer premise. So that's where you have where you have the lowest latency in the network, number one. So if you can do some of the processing right at the edge compute platform, rather than passing traffic towards the core network, it reduces the latency dynamically. So just thinking about some of the video workloads or CDN workloads, which require very low latency, the scalability aspect for the edge compute platform is very important on that, and therefore also the cost aspect. So if you can combine everything in a smaller footprint, which fits into a edge compute size, that's the main requirement to sustain the dynamics for the workloads to a cost-efficient point of view, rather than passing all the traffic towards the core network and then making networking decisions at that end when it's too late. So that's a big advantages as well, cost savings, using that at the edge compute side.
So the application is demanding an edge response, and the solution that we're providing here is a low-cost one. So our next question is programmable networks. In the edge cloud, you don't always require 10 or 40 or 100 gigabit interfaces. Do you see a trend where we get edge cloud area devices with a 1 gig interface and programmable forwarding planes? Anybody, we can open that question up to anybody here.
Yeah, so the aspect that we highlighted that here is for the access and aggregation point, it's usually the lower grade traffic flow, meaning 1 gig to 10 gig maximum, because there are many of these devices connected to the platform as an aggregation point. And then typically you use a framework from Intel using either DPDK or OVS, Open vSwitch, for the lower grade traffic flows. However, as soon as you aggregate it and you move it towards the higher traffic flow, that's when you need to be able to be more scalable and programmable to guide traffic throughout the network. Service chaining is a key element where we need the programmability for the higher end traffic flows to separate traffic for different workloads.
Great. Let's move to the next one, which is security included in the silicon white box as well beyond the compute memory, storage, and apps?
Say that again, please.
The question is security included in the silicon white box as well beyond the compute, memory, storage, and apps?
So the Barefoot Tofino is really the pipe, right? So all the security aspects in the networking point of view is the Barefoot Tofino together with the Noviflow cyber mapper is really doing the traffic mitigation, looking at the headers of the packets coming in, and then making the decisions if it needs further treating for deep packet inspections or not. And then the further traffic, the further processing is done by the FortiGate application. So that's where the security aspect is coming in. Until that point, we have 3 stages on that. So traffic coming in from let's say a SD-WAN device on the lower end will be aggregated, then moves over towards the Barefoot Tofino switch using the cyber mapper from Noviflow, which will then do the mitigation to see if traffics are known bad traffic or the whitelist and blacklist, as Jesper highlighted, and then pass traffic over towards the security application to the VNF from Fortinet to really do the additional processing for the packets. That's the level of security on that. Any other comments, Nick or Niklas or Jesper?
No, I think that's good, Sven.
No,
Great. Thanks,
that's good on our side. Maybe the question was about inside the hardware, like TPM, secure boots, and all that. I assume you.
So the TPM and secure boot is part of each individual compute node. So it's built into it as part of the platform infrastructure and the management layer of the platform.
So we're providing multiple layers of security there.
Yep, correct.
Here's a question for Prem. What benefit does having P4 programmability in the switchblades provide?
Sure. Thanks, Jennifer. Yeah, as I talked about in the presentation, there's quite a few benefits for, leveraging P4 programmability. One, P4 is an open language, and there's a huge community and a body of work out in the open that uses P4. So the end customers get to leverage that as well as the partners. And the other thing is, the biggest thing is the ability to adapt to changing needs, as well as future-proofing your system. As you can see, the way Noviflow has leveraged Tofino as well as FortiGate shows you the flexibility of the Tofino silicon that is brought forth by P4 programmability. So yeah, there's quite a few benefits, because of the P4 programmability, and we truly believe in the future. P4 programmable data planes will be key to building scalable, open, and future-proof and adaptable platforms. So HTCA 6600 is a great example of that. The work that Lanner has done, as well as Noviflow and Fortinet, right? So those are some of the things I would say are the benefits.
Thanks, Prem. Was there another comment there that I heard? Yeah. We are just about at the top of the hour, so we have, it looks like 5 seconds left. So I'm going to wrap it up there. We do have a lot of questions. Our speakers have copies of them, and we'll get back to everyone. And I'd like to thank everybody for joining in the webinar. You'll see all of the contact information for our speakers and for heavy reading at the back at the last two slides in the presentation. And I urge you also to complete the survey, which you should have in front of you at this point. So thank you all very much, and thank you all to our speakers. And have a good day, everyone. Stay well.
Thank you, Jennifer.
Thank you.
Thank you.
Bye-bye.
Bye.